Hello everyone. So the topic of today's discussion is short circuit time constant method versus open circuit time constant method to find out the FH and FL of transistor amplifiers. So first of all, we'll discuss SCTC, which is short for short circuit time constant. So this is used to calculate the FL 3 dB point of a transistor amplifier. So FL is limited by the decoupling caps that we have. This is the decoupling cap for decoupling the DC bias with the base voltage. This is to decouple RE, this is to short RE for AC, and this is to remove DC from the output. So these are decoupling caps that couple the DC values. Let's say CC2 is decoupling the DC value between this node and this node. So here the DC value is 0, but here you will have some DC value depending on the quiescent operating point. So FL is limited by the decoupling capacitors. So how do we find out the value of FL? Because the common plot will look like this. There will be some FL because this circuit will not have any DC gain, because at DC this will be open and this will be open, so the output will be 0 because the DC value of V6 will not be able to pass through CC1 since this is a DC blocking capacitor. So we'll have a frequency response that looks something like this because we will have 0 gain at DC. So now in order to find out the value of FL, we use a method that is called as the short circuit time constant. So what we do is we take this cap, we take these caps one after another, one at a time, and we short the remaining capacitors when we are considering one of them. So let's say first of all we consider CC1, the effect of CC1 on the value of FL. So when we consider the effect of only CC1 on the value of FL, we will short out CC2 and CE since we are only concerned about CC1. So now what we'll do is we'll write the time constant associated with CC1, which we term as tau1. So it will be just RC, where R will be the Thevenin resistance seen by CC1. So which means that we'll apply a voltage source between these two nodes and we'll calculate the resistance seen by CC1. So in this case, the resistance seen by CC1 would be from here we'll have R6 to ground, and from here we'll have, since this will be ground, since we null all the DC sources, this will be RB1 parallel RB2 parallel with the impedance from this node to ground, which will be R pi, since the impedance from the base of the transistor to ground is R pi. So we'll have RB1 parallel with RB2 parallel with R pi in series with R6, because between these two nodes these two resistances will be in series when we have a voltage source between these two nodes. So we'll just add up these two and we'll get RTH for CC1, that is the Thevenin impedance across the two ports where we have CC1. So this will have the value of tau1. Here we have shorted out these two nodes, therefore we did not have this RE factor while we looked into this node. We did not have the RE times beta plus 1 factor while looking from here because CE shorted RE out. That is why the impedance looking from the base to ground was just R pi. There was no factor of RE. Otherwise the looking in impedance has RE. But since CE shorted out RE because we have the method as short circuit time constants, we did not have RE here. Next up we find out the value of tau2. So when we will find out the value of tau2, we will consider only the capacitor CC2 and we'll short out these two capacitors, and we'll find out the Thevenin impedance looking from these two nodes. So it will be just RL to ground here, and over here we ignore the R0, so it will just be RC. So we'll just have RL in series with RC because we wish to calculate between these 2 points. So this will be the time constant associated with CC2. So now the last capacitor CE, will assume only CE and we'll short out these two capacitors, and we'll again find out the impedance looking from this node. Because this node is ground, we just need to find out the looking in impedance from this node to ground because one port is already grounded. So now this will be the looking in impedance over here, and then the in parallel with RE. So it will be RE in parallel with the looking in impedance from this side. That will come in parallel with RE. So the looking in impedance from this side will be, we will have RE that is from here. So we'll have RE when we look in from here, and all this impedance which is looking from this node to ground will be divided by beta plus 1, and the impedance that we see from this node to ground is simply everything in parallel, RB1 in parallel with RB2 in parallel with R sig, because CC1 is a short, in parallel with R sig, because we'll have this to ground, this to ground, this to ground, since CC1 is short, and V sig is also short because we null all the voltage sources and all the independent sources in the circuit. So V sig is ground, CC1 is short, so we'll have RB1 in parallel with RB2 in parallel with R sig, and when we since this is seen from base to ground, when we reflect it to the emitter, we'll divide it by beta plus 1. So the impedance looking here will be RE in parallel with small RE, because we look from this side, and this is small RE in parallel, small RE added with all this impedance reflected at the emitter, so it will come in series with RE, because RE was already in series with the emitter. So all this impedance reflected back to the emitter added to small RE, and that will come in parallel with RE1, because the impedance seen from here was from this point to ground, and RE is also from this point to ground, so RE will naturally come in parallel with the impedance seen from this node to ground. This here is the impedance seen from this node to ground, which is simply RE plus all this impedance reflected to the emitter by dividing it by beta plus 1. So we'll have RE, we'll have tau E. Now the method of short circuit time constant says that the value of FL, stating without proof, will be given by this expression. FL will be 1 over 2 pi times 1 over tau 1 plus 1 over tau 2 plus 1 over tau E. So since you have found out all these time constants by seeing one capacitor at a time and shorting all the other capacitors, we get these time constants, and then once we get these time constants, we can find out the value of FL that we have over here by this expression. So this will give us the value of FL, which is dominated by the decoupling capacitors. So now this is all about SCTC. Now we will contrast it with another similar method which is called as OCTC. So OCTC is a method used to calculate the FH of an amplifier, because an amplifier will not have this flat band till infinite frequencies, because what will happen is the internal capacitors of the MOSFETs will short this node to ground and every node to ground, so that the gain at very high frequencies will drop down to 0, because the intrinsic capacitors of the MOSFETs will short the input to ground. So we'll have 0 gain at infinite frequency, so there will be some 3 dB points. These are the 3 dB points that we are talking about, and this 3 dB point will be at corner frequency of FH, which will be influenced by the intrinsic caps of the MOSFETs. So we'll take an example to show how do we calculate the value of FH, which in turn will depend on the intrinsic caps. So we have a cascode structure. We have a CSCG cascode, and we'll find out the value of FH for this structure. So the method is slightly different. Now we'll calculate open circuit time constants, which will mean that we'll calculate the time constants, but we'll open the capacitors when we consider one of them. So let's say first of all we consider CGS1. So when we consider CGS1, what we'll do is we'll open circuit all the capacitors. So this will be open, this will be open, this will be open, and this will be open. So we'll open circuit all these capacitors, and we'll only focus on CGS1. So what will be the impedance looking from G1 to ground? That will be the Thevenin resistance for CGS1 in order to calculate tau CGS1. So that will just be R sig, because CGD1 is open and this impedance at the gate is infinity. So we'll just have R sig with CGS1. So now CGS1 is done. Next up we'll pick up CGD1. So CGD1 is the most trickiest part, because analyzing the impedance between G1 and D1 is usually hard. So what we'll do is we'll use the Miller theorem to break CGD1 into two parts. So we'll have CGD1 divided by the gain, which will approximately be CGD1, and we'll have a capacitor from G1 to ground, which will be CGD1 times 1 plus A, where A will be given by GM1 times RD1, because A will be the gain from this node to this node, because the capacitor is between these two nodes, and the gain from here to here is GM1 times RD1. So this capacitor will be, A will be GM1 times RD1, and RD1 will be given by the impedance seen from drain. So that will be this parallel with this. So this is RO1, and this will be the impedance of a common gate stage, the input impedance, which is given by RL plus RO2 by 1 plus GM2 RO2, where RL is the load resistance. Simple looking in impedance at the source of a MOSFET, or the input impedance of common gate stage. So that will be RD1. So when we see this CGD1, we'll open circuit everything else. So for this CGD1, what will be the RTH? It will be similar to the RTH seen by CGS1, because these two are in a similar position. That will only be RSIG. So we'll have CGD times RSIG and times this 1 plus A factor, that was A was GM1 RD1, as you can see here. So it will be similar to CGS1, because the RSIG will be same, because these two are in a similar position. Now for CGD1, that is here, which was CGD1 into 1 by A factor, that 1 by A we can assume to be close to 0, because A is large, assuming GM RD1 is large, such that we can neglect 1 by GM1 RD1 with respect to 1. So with this, what will be the case? So we can club these two capacitors. So we can have CDB1, CGD1 as well as CGS2, because all these capacitors are from D1 to ground. So we can club these three, then open circuit everything else, and then find out the impedance seen from D1 to ground, because this node is already grounded. So we just need to calculate the impedance seen from D1 to ground. Then the impedance seen from D1 to ground will simply be RD1. We have already violated RD1. So we'll have this expression. Now the last MOSFETs will be, so we have completed the discussion with CGD1, CGS1, CDB1, CGS2. Now CGD2 and CL are remaining. CL will also be a low capacitor. It will not be a decoupling capacitor. So the question might be, why are we not considering the decoupling capacitors? Because they are anyways open circuit, and these are mostly integrated circuits, so usually they do not have any decoupling capacitors because they are huge. So next up we'll analyze CL and CGD2, which is from this node to ground. So anyways these two can be clubbed, because anyways these are from D2 to ground. So we'll analyze this and we'll see the impedance looking from D2 to ground. That will be the Thevenin impedance for CL, and CG2, that will be the looking impedance from D2 to ground, because anyways this node is at ground, so we would only need to calculate the Thevenin impedance seen from D2 to ground. That will be termed as RD2, and that will be just the output impedance of a cascode stage. So that will be RL in parallel with the impedance seen over here, which is given by the standard formula, approximately GM2 R1 R2. You can add up these two terms if you want a precise value. So this in parallel with RL will be RD2. This RD2 will go with CL plus CGD2 since they are in parallel. So we will have this final expression. So now you might have noticed that since I have calculated this, I am summing this up. This is slightly different as compared to SCTC. SCTC, FL is given by 1 over 2 pi times 1 over tau 1 plus 1 over tau 2 plus 1 over tau e. Here FH is given by 1 over 2 pi tau h, where tau h is the sum of all the time constants. So this is a bit of a contrast that we have here. These two expressions are not exactly equal. Here we sum up the inverses of the time constants, and here we sum up the time constants and then we take the inverse. That will be the approximate value of FH. So I think that is it for the video. I hope now you guys can calculate FL and FH for any transistor topology that you have been given. This is one of the most complex topologies, I think. So if you have understood this, I think it will be good to go for calculating the responses of common source or common gate or common drain for FH. And also CE is a good example to calculate FL. So you can go on to calculate FL for any other transistor topology that you find. So I hope this video gave you an idea about what are the contrasts between OCTC and SCTC, when do we use them, what are they for, why do we have FH and FL, how do we write FH and FL with the ease. So the basic thing that you need to know is how do we calculate the resistance seen between 2 points or from one node to ground. So that is something that should be very handy. And once you know that, just open the other capacitors or short the other capacitors, find out, get the individual time constants, plug into the formulas of FL and FH, and you will get the value of FL and FH. So that will be useful because you will be needing to know what is the approximate frequency response of your amplifier, and the flat band must fall at your required range of frequencies. So I think that is it for the video. Thank you for watching.